I have one more sort of, I guess, line of questioning before we get to Venus. And one of the reasons that I want to go through all of this does go back to the Avi Loeb issue. Is I just want to make sure how clear, like, hard science is going into this, and you're not just seeing aliens everywhere, basically. But what I'm wondering is what daily work on these problems looks like, because I think that's very interesting for non-scientists. Because I'm wondering, is it a lot of time spent in front of a chalkboard, or the kind of fantasy lay people have of scientists with beakers full of colorful liquid, or tinkering around with computer code, modeling different situations? Like, what sort of thing, other than the pleasure of having conversations with people like me on a workday, are you doing related to these problems?
So no beakers, but yes, it's a lot of modeling. So a lot of modeling and a lot of emails and video chats with lab people who do have beakers, just not phosphine. And the main game is all in the service of not missing life if you're looking at it. And so the game is, you have this light from a planet, and that light is composed of all the molecules that are in there. And the game is saying, okay, which of those molecules shouldn't be there? If they shouldn't be there, what are the explanations? And are we even sure we got it right? Because the signals from one molecule can look like the signals from another. And so the step is, what molecule could cause a signal? And that's really hard. And so it's a lot of looking at observations, a lot of injecting fake noise into it to see if it goes away. And if you could assign a signal to a molecule, you go, okay, what is that molecule doing there? And a lot of times you can say, well, we know the star and we know other molecules, so it could just be photochemistry. The light hits it, it breaks it, now you have products, and these become reactants for new molecules. We can explain it away. This is what happens. There's light, there's a planet, you get this molecule. That's not surprising. Or let's say in the Avi Loeb extreme, we go, that signal, I know that signal, that's CFCs. CFCs, not even Jupiter and Saturn can make. Those are molecules that only a intelligent civilization with a death wish would make.
Chlorofluorocarbon?
Exactly. And so these outputs from industrial activity, like CFCs, would be very quickly would be like, well, I think there's life there. Probably not for long. CFCs are not great for a planet, but there's life, there's intelligent life, and they're probably going to kill each other. And that's incredible. So you go from going, oh, there's a molecule, that signal is definitely that molecule. Maybe they have oceans, good for them. Or there's a molecule that could only be in life. Most molecules fall somewhere in between these two. Phosphine and isoprene are closer to the CFCs than to the molecules that just happen naturally in the universe, but they're not there. There's still explanations for them that don't involve life. And so most of my work is thinking of this entire list of molecules between water and CFCs. And that list is 16,367 molecules. And so I spend all of my time, when not talking to people like you, figuring out, what does that signal look like? Could we get it wrong if we saw it? And if we see it, what could it mean? And it takes about half a decade to study each one of these molecules. So you can see how these numbers are not in my favor. But that's what I do every day. I try to chip away at that list.
Yeah, my understanding is that this methodology has currently got us in a really tight bottleneck, because there are far more gases, as you've just indicated, out there that could be indicative of life than we currently have the signatures to detect. And it took you 5 years just to get one of them. And
that's to get the signature. It took me many, many more years to then figure out, if we did see it, phosphine in this case, what would it mean? And to do that for every other molecule is just completely overwhelming. I can't train people fast enough, and I don't have the money to train people fast enough. And so it's easy to let it stress you out. I'm very zen about it, because it's so impossible a problem that there's no hope I could solve it. And that's a relief.
But I have seen, though, which is very cool, that you're doing a ton of work getting young people involved in astronomy and having them do real research, which is quite laudable, if I don't say so myself.
Thank you. A lot of astrophysics feels very selfish. I could have chosen many sciences, but I chose the one of me, looking into the skies, contributing nothing to humanity. And so the very least I can do is train the next generation.
Mm-hmm. And so I have a couple more questions about the modeling. So again, just to give the non-astrophysicists like me a better idea of what it means to say you're modeling something. So what goes into modeling a planet's environment on a computer? What does this look like? Because it's not like you're making a playable video game environment, which is what I think people might
That would be
intuitively
nice.
think of.
We should put some work into getting like actual visuals to the things we're doing, because it would be so cool. But we barely have the GPUs to run the things we want to run without trying to
Right. It takes
actually
huge computer power.
huge computer power. I mean, when I was doing just the phosphine spectra, so just one molecule, not the whole atmosphere. I remember my temporary files that I had to move around were 11 terabytes, just of my temp files, not the actual outputs or my inputs. Those are just things that I had to like shuffle along as I calculated these giant matrices that would break computers everywhere. I would have to time my calculations to the average length of time that electricity doesn't get cut off. So it was like any calculation took longer than 3 months to run, I just couldn't do. Because I knew the odds that something would go off within those 3 months, and then you would have to start from the beginning. And that's for one molecule. When we're modeling a planet, we have to cheat. We have to really simplify things. And so we presume a certain production of molecules at a surface, and sometimes we can like sprinkle some a little higher up. And then we have the code input every type of reaction between every molecule at that temperature and pressure. And for every bit of the atmosphere, which we cut into these like envelopes, you can imagine like spherical envelopes. And for each section of the envelope, we figure out, okay, what would these reactions lead to at this temperature and pressure with this much light making it from the top? And then we do this for every layer, and we let the layers interact. And then we see, okay, if you observe the third most layer from space, what would that look like? And that's kind of the simple explanation to what we do. But this is a problem that grows very quickly, as you can imagine. When you put more molecules in, more different types of light from the star, winds, convection cells, production rates that vary between day and night, the volcanism, lightning, it becomes a really intractable problem to simulate a planet, as it should be. It's a really complex place.
Mm-hmm. Right. Yeah. So, given the computer power constraints and the fact that you can't completely model a system with anything smaller than the system itself, which for a planet, the amount of information involved is just absurd. No computer obviously could handle it. So just the last thing, are there any relevant variables that play a part in your models beyond some of those that you mentioned, like temperature and pressure, or light because of its role in breaking down phosphine, or lightning and volcanic activity? Or are there any other major ones?
The reaction rates. And I say major ones because you need to know how molecules created and destructed. Say if I find a molecule, if there are many ways of it being produced within the photochemistry and the geochemistry of that environment, then we'll never be able to pinpoint it as a production, an output of life. And so for that, we need to know reaction rates. And on Earth, we know very few, and only for the molecules on Earth. And so whenever we're simulating a planet, 100% of the time, we have to just make up reaction rates because we don't know them. No one's measured them. And that can really change what the output of this model is, which is crucial if we're trying to then observe a planet and say, well, our model of that planet matches the observation, so we must be right. It's really easy to get it wrong and to miss it.